folks, Mrs. White here. Hoping things went well with graphing square roots in our previous lesson. If you didn't show up for office hours, that doesn't mean you missed out on it, folks. Reach out for more help. I'm more than happy to help you. I also want to remind you that I have office hours twice a week, right? So you can show up on Friday and ask questions about Monday's stuff if there's still some confusion there, okay? Feel free to do that. This will be our last lesson before April vacation. Next week, you guys have no new released material, so enjoy some extra time with your family, making sure you get yourselves outside, right? It seems like it's being a pretty good spring right now, so spend some time outdoors, soak up some of that sun. Just so you have an idea of rundown, we're starting section 5-6 today. 5-6 is actually the last new learning we're going to do, but I broke it into a couple different flipped lessons because it can be kind of dense. So today we're going to focus on solving radical equations. When we get back from break, we'll review this briefly, and then we're going to do radical inequalities. Both of those are in section 5-6. I thought it would be best to split it into 2 separate class sessions and 2 separate practice sessions so that you can really make sure you are doing a good job at both of them, okay, since you're going to see both of them on the test. So what that means for after April break is we're going to review this. We're going to do about that 1 week when we get back will be new learning. The following week will be review for test and taking a test, which will have to be proctored by a parent at home. So I'm going to be reaching out to your parents after break, letting them know kind of what we've accomplished and asking them for help in proctoring that so that I can just send the test to them and they can keep an eye on you and make sure that you are only using a calculator and Scrap as you solve. Anyways, long story short, that's what's coming down the pipeline, okay? We're going to start off today with a quick review of some of the other skills from Chapter 5, and then we're going to hop into talking about how do we solve radical equations, what are the 3 steps to solve, what are extraneous solutions, and how can we come across them or check for them. Where do fractional exponents come from? And I have a short little Khan Academy video. It's actually like 5 minutes that I'm just going to play for you during my flipped lesson because it has some good information in it, and I like how he does that. And I want to remind you, if you're ever struggling in any of our lessons, you know, check out what they have on Khan Academy. They might have extra practice that you can try to do or a video that explains it differently that's starting to work, you know, better for you. Please, 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 that's a resource for you now more than ever, okay? Then we'll just do a bunch of practice before this lesson ends. That'll be kind of where we end up. You do have homework over April break / if you finish it on Friday before April break, you have no homework. It's pretty hefty. I'll be honest with you. It's bigger than some of the other assignments. I want you to do 23 through 49 odd in your book. And that focuses entirely on solving radical equations. So everything there has to do with an equal sign. I really want you to practice a lot. I want you to be really good at it so that when you come back after break, it's still kind of solidified in your noggin and you don't have to spend a bunch of time reviewing to be able to get there, okay? So let's hop into talking about some of the stuff we've already covered in Chapter 5. So this first one looks at compositions of functions. And this is f of g of x. And what that really means is if we take our f function and instead of x in it, we plug in g of x as our x and then simplify. So that's what we're going to do. Here's our f of x function. Here's our g of x function. We're going to plug this in for the x in our f function. Plug the g into the f function and then simplify. And this is actually going to be a pretty good amount of work. So my f function starts out with a 2 and then it has x. And again, we're replacing the x with this whole binomial here. So 8x squared plus 3x. And then it ends with this squared. So I'm going to put that on top. Now we need to simplify this, and it looks like it's not too bad, but I want to point out to you this is a binomial, and it's going to be times itself. So in order to solve that, we have to do double distribution, excuse me. So we have 8x squared, plus 3x times itself, right? 8x squared plus 3x. And in order to do this times this, I have to, you could say FOIL, you could say double distribute. That's what I like to say is double distribute. So I'm going to send that there, and this here and here. So I'll keep my 2 out front. Okay, I'm just bringing it down or over every time. 8x squared times 8x squared is going to be a 64x to the 4th because I add my powers. 8x squared times 3x is going to be a positive 24x to the 3rd. Then I'm going to have a 3x times an 8x squared, which gives me another positive 24x to the 3rd. And then my last piece is going to be 3x times 3x, which is positive 9x squared. I should simplify these two pieces. 24x to the third and 24x to the third is going to give me 48x to the third. So I actually have a trinomial here, 64x to the fourth plus 48x to the third plus 9x squared. Now I need to take all of that and times it by 2. So I'm going to distribute this 2 here and way over here. So 2 times 64 is 128x to the fourth. 2 times 48 is 96, so I have a positive 96x to the third. And then 2 times 9 is positive 18x squared. And that's my answer. I just need to add my label in front. I did f of g of x, and this is what I got. Boom, there is my solution. Okay? Now I don't have to do the other composition. They didn't ask me to, just this. Next, I'm asked to find and graph this inverse. So to start off with an inverse, I replace my y with my x, and I replace my x with my y. Then my next task will be to get my y alone and positive, and that's going to be my resulting inverse equation. So before I can get rid of this squared or this 1 or get into that parentheses, I need to get rid of the stuff on the outside, so I'm going to minus 3 minus 3. And I'm left with x minus 3 equals y plus 1 squared. Now, because the squared is the only piece that's left here besides the plus 1, but I can't get to that till I get rid of this, I'm going to do the inverse of squaring, which is square rooting. Cancel, cancel. Last step, I'm going to minus 1 minus 1. I have square root of x minus 3 minus 1 equals y. Now, when we're asked to graph this, we should think of our parent function. This is a square root. This is what we just did last class, okay? This is going to be a shift to the right 3 and down 1. So instead of starting at 0, 0, I'm going to go to the right 1, 2, 3, and down 1. Then I'm going to go up 1, forwards 1, up 1, forwards 1, 2, 3. And there's my graph. So now let's talk about the new stuff we're going to be covering in this section, which is solving radical equations. So there are 3 general steps to solve radicals, and I want to point out to you the word radical does not mean square root. A square root is a radical, but not all radicals are square roots. A radical is going to be anything that has a radical sign, and it could be this, which is the square root. It could be a cube root. It could be a 5th root. It could be a anything root, okay? And we might call that the nth root. It's any sort of radical symbol that's going to be tied to a root. Now this number right here in front, and even this letter n that stands for any number, this is called our index number, and it defines what type of root it is. So if a 3 is here, it's a cube root. If a 5 is here, it's a 5th root. If a 12 is here, it's a 12th root, okay? All of these are radicals, and we're going to be able, hopefully, to be able to tackle each of these types of problems today. So your first step is to kind of isolate your radical on one side of the equal sign. So you're going to get your radical alone on one side. Now that's really easy to do if you have one radical symbol, like in our first example. But looking at our second one, we have a radical on both sides. Instead of worrying about getting them combined, you cannot combine them. You're just going to get one of them alone on one side of the equal sign. After you've done that, the next step is to raise each side to a power. Oh, my pen is not working today. I apologize. Raise each side to the power of your index. And you could say that is the actual power of your radical. But we just talked about our new vocab term, right? So this is our index number. So if we're dealing with a cube root, we're going to get our cube root alone. Then we're going to raise both sides to the 3rd power. If this is a 5th root, I'm going to raise both sides to the 5th power. If this is an nth root, I'm going to raise both sides to the nth power, if that makes sense, okay? That's how we're going to do the inverse operation here to cancel out the radical sign. The last step, once you've canceled out your radical sign, is to isolate your variable. That way you're actually finding your final solution, right? You want to get x alone and positive, and you can finally do that once you've gotten rid of your root sign. Okay, so get your radical alone on one side, raise each side to the power of your index, and again, that index number defines what your radical is, and then lastly, isolate your variable, get it alone and positive. Now, there are going to be times that we're going to get solutions in this chapter that are going to be potentially extraneous. So an extraneous solution means that you get an answer that doesn't work. Okay, it's impossible. So extraneous can happen two different ways in these types of problems. And extraneous is going to exist later on also, okay? So an extraneous could happen when you end up with a negative number under your root sign and when your root is an even, okay? Now, if you have a negative number under a cube root, that's fine. A negative times itself 3 times works, okay? But a negative under an even power would mean that that negative sign is going to cancel out with a pair. And so you can't have a negative underneath. If you ended up plugging in a number and you got a negative underneath an even radical, then you're going to end up with an extraneous solution. It will not work. The second thing that could happen is that when you plug it in, it just doesn't equal, okay? Remember, if I were to plug in something here and solve this, it should equal 7, right? If I go to check it and it doesn't equal 7, then I have now found an extraneous solution, and that could exist for a couple different reasons, okay? It could have to do with just the way that the equation's set up. I will tell you at least one of the ones down here is going to give us a solution that's going to be extraneous. So for now, to check for an extraneous solution, okay, just to check for it, you're just going to literally plug in your answer and make it work. And make sure it works. I am so guilty. That says plug it in. That is horrible. Okay. Plug it in. Yay. Okay. I am super guilty of being the person in school who never checked their answers. I get it. Okay. I totally understand. It's a lot of work. Most of the time you check it and it works. I will tell you in this unit, in this homework that you're going to have tonight, there are going to be a couple times that when you plug it in, it will not work. It takes 1 extra minute. Do it with mental math, just double check and make sure that your answer isn't accidentally extraneous, okay? And it's possible that it is, so please, please double check. So let's look through at solving, and then we'll check all of our answers to make sure that one of these two situations isn't occurring. So first step first, our step above is to get our root sign on one side of the equal sign by itself. So if I look here, I've got x plus 2 under the root sign and then a plus 4 on the outside. I got to get rid of this plus 4 by minusing it to each side. Then I'm left with the square root of x plus 2 equals 7 minus 4 is 3. At this point, folks, hopefully you're like, all right, my root's alone. Step 2, even though I don't have an index number of 2 here, I know it's a square root, okay? I'm going to square both sides to cancel out my root, just like square root property we did in chapter 3 with quadratics, okay? Yeah, so now I have x plus 2 equals 3 squared is 9. Lastly, I'm going to minus 2, and I get x equals 7. Now, this is my solution right now. I want to make sure that it's not extraneous, meaning that if I plug it in, it actually does work. So I'm going to plug it in. There's my 7. And I'm going to start by doing 7 plus 2 under my radical sign, which is 9. Square root of 9 is 3. 3 plus 4 is 7. It works, okay? So I'm really confident in that answer. Let's take a look at our next problem, okay? I'm going to try to get my x alone, or excuse me, my root alone on one side. And if I look here, this already has a root alone, but it feels weird because there's another root here. Who cares what's on this side right now? Even if there's another root, you cannot add it over here and have it combine, okay? You cannot add a radical and have them be together unless they're the exact same underneath, okay? This is an x minus 12. This is just an x. They are not the same radicand. They cannot be put together, okay? So instead, once you get one of your roots alone on one side, that's where you're going to move right to step 2. So I look at my index number. There's nothing. That implies that it's a square root. I'm going to raise both sides to the second power. Now look what I did on this side over here, right? I have to take this whole side and square it. This side's nice. Those cancel. I'm left with x minus 12 equals this. I hope you're saying, oh no, because you're realizing it's a binomial and it's being squared. When you have a binomial being squared, you have to times it by itself. And the way we do that is by doing double distribution, Or you guys, some of you like to say FOIL, okay? So I'm going to do 2 times 2. We just did this in our sim again. I know we're dealing with roots, okay, and that's a little different, so we'll talk about that as we come across it. But generally speaking, we're just going to FOIL it. So 2 times 2 gives us 4. 2 times negative 1 square root of x. I do my constants. 2 times negative 1 is negative 2. And then I'm going to treat square root of x like its own little variable. It just stays square root of x. Then I have this negative square root of x times 2, which gives me another negative 2 square root of x. And then lastly, I have a negative times a negative, which will be a positive. And then I have square root of x times square root of x. So I could say I have square root of x squared, right? I have a square root of x times itself. Well, now I need to simplify this, all right? I want to point out to you that square root and square are going to cancel, and this is just going to give me x. And this 4 is just a constant. So I have a 4, I have a positive x, and then I can combine these two together because if we look, our radical sign is identical, right? I have negative 2 square root x's. I have another negative 2 square root x's. So together I have negative 4 square root x's, if that makes sense. I have negative 4 square root of x. So now I'm hoping you're looking and you're saying, all right, did that actually do anything? It looks more complicated. It does, but now we only have one root. Before we had a root here and we had a root here, right? Well, by squaring this side and this side, we got rid of one of our roots. Now we have just one left. So I'm going to start back at the beginning of my 3 steps. I'm going to come back to number 1. I'm going to get my radical alone. I'm going to raise each side to that power, and then I'm going to isolate my variable. So I'm going to get this root alone. I got to get rid of these things before I can get rid of this. So I'm going to minus 4, right? I want to get it away from this side to get this piece alone. I have x minus 16 equals x minus 4 root x. I'm going to minus this x. It's on the outside, right? Over here. Well, x minus x, that's kind of nice. They canceled. I'm left with negative 16 equals negative 4 root x. Now, this negative 4 is not under the root, so I need to get rid of it. It's being multiplied. I'm going to divide by negative 4 on both sides. Those cancel. 16 divided by 4 is 4. Those both cancel, and I'm left with a square root of x here. Now, root is alone on one side. I can square and square, and I get that x is going to equal 4 squared, which is going to be 16. Okay? 4 squared, which is going to be 16. Now I need to check and see if this is an extraneous solution. Now what's different about this problem is that there's a root on both sides. So I have to plug my 16 in here, and I need to plug my 16 in here. So let's simplify this side first. 16 minus 12 is 4. So I have square root of 4, which is the same thing as 2. Okay, square root of 4 was the step before, which equals 2. Over here, I'm going to plug in a 16 also. So my first step is actually to do square root of 16 and then do 2 minus that. So the square root of 16 is 4. So I'm left with 2 minus 4. Sorry about that. 2 minus 4. And 2 minus 4 equals negative 2. Now, does 2 equal negative 2? No, it does not. This 16 is not a solution. It is extraneous. Okay, that's how we would describe it. It's an extraneous solution. Now, our answer isn't that our answer is extraneous. We would say that there's no solution. Okay? There's no solution because the number we got is extraneous. It's not going to work. So those both had square roots. Remember, we could have any radical sign, and we would solve it the same way. But looking at this one right now, I'm sure you're like, oh, great. What is going on here? One, there's no roots, and it feels like there should be because everything that we just talked about has to do with roots. Second, there's a fractional exponent, and not only do you not love fractions, but having it in an exponent probably feels pretty stressful, okay? So we're going to take a little side lesson. We're going to watch a 5-minute video from Khan Academy to kind of set our mind at ease and explain what that little exponent means. We'll come back here, just fill this out, practice putting things in exponential and radical form real quick, and then we'll go back and solve that problem.
We already know a good bit about exponents. For example, we know if we took the number 4 and raised it to the third power, this is equivalent to taking 3 4s and multiplying them. Or you could also view it as starting with a 1 and then multiplying the 1 by 4, or multiplying that by 4 3 times. But either way, this is going to result in 4 times 4 is 16, times 4 is 64. We also know a little bit about negative exponents. So for example, if I were to take 4 to the negative 3 power, we know this negative tells us to take the reciprocal 1 over 4 to the third. And we already know 4 to the third is 64, so this is going to be 1/64. Now let's think about fractional exponents. So we're going to think about what is 4 to the 1/2 power. I encourage you to pause the video and at least take a guess about what you think this is. So the mathematical convention here, the mathematical definition that most people use, or that frankly all people use here, is that 4 to the 1/2 power is the exact same thing as the square root of 4. And we'll talk in the future about why this is, and the reason why this is defined this way is it has all sorts of neat and elegant properties when you start manipulating the actual exponents. But what does the square root of 4, especially the principal root, mean? Well, that means, well, what is a number that if I were to multiply it by itself, or if I were to have two of those numbers and I were to multiply them times each other, that same number, I'm going to get 4. Well, what times itself is equal to 4? Well, that's, of course, equal to 2. And just to get a sense of why this starts to work out, well, remember, we could have also written that 4 is equal to 2 squared. So you're starting to see something interesting. 4 to the 1/2 is equal to 2. 2 squared is equal to 4. So let's get a couple more examples of this, just so you make sure you get what's going on. I encourage you to pause it as much as necessary and try to figure it out yourself. So based on what I just told you, what do you think 9 to the 1/2 power is going to be? Well, that's just the square root of 9, the principal root of 9. That's just going to be equal to 3. And likewise, we could have also said that 3 squared is, or let me write it this way, that 9 is equal to 3 squared. These are both true statements. Let's do one more like this. What is 25 to the 1/2 going to be? Well, this is just going to be 5. 5 times 5 is 25, or you can say that 25 is equal to 5 squared. Now, let's think about what happens when we take something to the 1/3 power. So let's imagine taking 8 to the 1/3 power. So the definition here is that taking something to the 1/3 power is the same thing as taking the cube root of that number. And the cube root is saying, well, what number, if I had 3 of that number and I multiply them, that I'm going to get 8. So something times something times something is 8. Well, we already know that 8 is equal to 2 to the 3rd power. So the cube root of 8, or 8 to the 1/3, is just going to be equal to 2. This says, hey, give me the number that if I say that number times that number times that number, I'm going to get 8. Well, that number is 2, because 2 to the 3rd power is 8. Do a few more examples of that. What is 64 to the 1/3 power? Well, we already know that 4 times 4 times 4 is 64. So this is going to be 4. And we already wrote over here that 64 is the same thing as 4 to the 3rd. I think you're starting to see a little bit of a pattern here, a little bit of symmetry here. And we can extend this idea to arbitrary rational exponents. So what happens if I were to raise, let's say let me think of a good number here. So let's say I had 32. I have the number 32, and I raise it to the 1/5 power. So this says, hey, give me the number that if I were to multiply that number, or I were to repeatedly multiply that number 5 times, what is that? I would get 32. Well, 32 is the same thing as 2 times 2 times 2 times 2 times 2. So 2 is that number that if I were to multiply it 5 times, then I'm going to get 32. So this right over here is 2. Or another way of saying this kind of same statement about the world is that 32 is equal to 2 to the 5th power.
So now that we've seen that Khan Academy video, we kind of have an idea of how or where these fractional exponents come from. That denominator right there gives us an idea of what our index number is, right? That number outside of our root sign. And so if we kind of take this idea, this b to the 1/2, and say, okay, well, based on what we saw, that would mean that it's the square root of b. Okay, and in order for that to be true, then if we squared it, things should cancel out, right? If we have the square root and a squared, we should just get b, if that's the case. So we can kind of take a look at this problem and prove that, okay? This power to a power is just one of our normal exponent properties, and when we have a power to a power, we multiply. So we go across the top, across the bottom, we end up getting 2/2, which is 1. So we can see, oh, when we square this, just like if we squared a square root, we do end up canceling it out to get just b. So that is using kind of our principal root idea when we have 1 as a numerator and then our index as a denominator. So when we put something in radical form, we're taking it from that fractional exponent and making it a radical. So the first thing you're going to do is you're going to take whatever your base number is, x, that's going to be in your radical sign. The denominator is going to be your index number. And then this numerator would be the power attached to your x. So this just becomes the 6th root of x. Okay? And we can also work backwards. We can take something that's a radical and write it in exponential form, which means that it's going to have an exponent. Okay? So if we have the 4th root of z, okay, we know that whatever's inside here is going to be our base, so that's going to be our z. It's going to hold up an exponent. 4 is going to be our denominator, okay? And then our numerator is always whatever power is attached to your inside here, which is just 1, so z to the 1/4. So again, these are called principal roots because they all have that one exponent as our numerator, the 1 is our numerator in the exponent, and that's because each of these had 1. But we can also do that with other powers underneath. So if we were trying to figure out what the heck does a equal, and there's a proof for this, we're not going to stress out about it right now via remote learning. We could look at it as, we know a is going to be a fraction. The denominator of a is always going to be your index. And the numerator is whatever is attached to your radicand there. So it's going to be a 5th. So 8 to the 5/3 is the exact same thing as 8 cube rooted, okay, because that's our denominator, but there'd have to be a 5 in here. Okay, so take a second and think about this one. What would this one have to be? What would a have to equal so that it became this? Okay, our denominator would have to be the index. And our numerator is whatever power is attached on the inside here, so squared. Okay, so we would have that 6 to the 2/5 power is the exact same thing as 6 squared 5th rooted. So let's fill in our blanks over here, okay? If we have 2 to the 3/4, this 4 is going to be our index, and this 3 is going to be our exponent on the inside. Similarly here, this 1 is going to be our numerator, is always the power on the inside, and we don't have to write a power of 1, we could just leave it as 4, and then 3 becomes your index number. So changing things from exponential form to radical form isn't hard as long as you know kind of the rules behind how that fractional exponent works. So now let's go back to that example we were looking at beforehand, okay? I see this as a fractional exponent and it's attached to this parentheses, okay? So this is like my base, there's my exponent. Hopefully you're thinking right now, I know what this is, Miss White. This 3 in the denominator means we're going to be dealing with a 3rd root, and this 1 would be like the exponent outside of this. So we actually could rewrite it as 2 times the cube root, right, for the 3, of 6x minus 3. On the outside is a minus 4, and then equals 0. Okay, so what we want to do is if we have a fractional exponent, our first step really should be to write it in radical form. Once it's in radical form, you can follow the following 3 steps that we had already outlined. Okay, so now that it's written with a cube root, I'm going to get my radical alone on one side, and then to cancel out the cube root, I'm going to cube it. So to get this alone, I see it's being times by 2, and there's a minus 4. So my first step has to be to add 4 to both sides. Then after doing that, okay, so I can imagine there's a plus 4 here and that's canceled. I'm going to divide by 2 just to cancel out the times by 2. I don't divide this by 2 and this by 2. This is a mono right now, technically, right? It's a 2 times a chunk. So I'm just going to divide by 2 here and divide by 2 there. This will cancel these items out. Now I'm left with the cube root of 6x minus 3 equals 4 divided by 2, which is 2. Now, because it's in that radical form, it's easy to see, okay, my index is 3, so to cancel out a cube root, I'm going to cube it. I have to do that to both sides. I have 6x minus 3 equals 2 to the third, or 2 times 2 times 2, which is 8. I'm going to add 3. I get 6x equals 8, 9, 10, 11. Divide by 6, divide by 6. And my answer is that x equals 11/6. Now, just because you get a fraction doesn't mean that you did anything wrong, okay? I want to point that out. A fraction isn't a wrong answer here, okay? Fractions are going to have to happen more often than not, especially if problems are kind of being thought up either kind of on random, or if the problems are resulting from a word problem. A lot of the times you're going to get decimals and fractions. We still need to check and make sure this answer works and that it's not extraneous, so we're going to plug it in here. 11/6. So 11/6 times 6, well, the times 6 and the divide by 6 cancel. I'm left with 11 minus 3, which is 8. So right now I'm going to kind of bring this, let's change our colors so we can keep it organized. I'm going to bring my extraneous work down here in pink. I still have the 2. We said we had 11 minus 3 here, which is 8 to the 1/3 minus 4 equals 0. So 8 to the 1/3 is the exact same thing as the cube root of 8. Well, the cube root of 8 means what number times itself 3 times equals 8? That's just 2. So I have 2 times 2 minus 4. Well, 2 times 2 is 4, and 4 minus 4 is 0. It works. It is not extraneous. X equals 11/6 is my answer. Okay? So from here, we're just going to continue practicing, okay? Especially with roots that aren't square roots. So let's take a look at this one. We'll solve this one together slowly, and then I'll give you a minute or two to try to work on this one on your own, and I'll put my work up here very quickly and quietly, and then we can compare answers. So first things first here, I'm solving it. There's an equal sign. I need to get my root alone, and they're showing this root is in parentheses, so I need to get rid of the 3 and the minus 6. My first step is to add 6, and then divide by 3, divide by 3. So in my head or on my paper, I'm thinking this. I have a 4th root of 2n plus 6. I've already added 6. Then I've divided by 3, right? So I currently have a 2 over here. Now here's where our kind of new learning comes in, right? It's a 4th root. So to cancel a 4th root, I raise it to the 4th power. Okay, these 2 cancel, which is nice, and I have 2n plus 6 equals 2 to the 4th, or 2 times 2 times 2 times 2. 2 times 2 is 4. 4 times 4, right? 4 times 4 is 16. I'm going to minus 6 minus 6. Divide 2, I get n equals 5. Okay, so right now this feels like my answer. I should double check and make sure it's not extraneous, especially if one of my solutions is a no solution, right? So 2 times 5 is 10. 10 plus 6 is 16. So what number times itself 4 times is 16? Well, we actually already calculated that. It's 2. 2 times 3 is 6, and 6 minus 6 is 0. So yes, it works. The answer is 5. Give yourself a second here. Remember, this is a 1/4, right? So your first step should be to write it in its radical form, okay? I'm going to be quiet and put my work up, and then we'll chit-chat about the answer. All right, so I ended up with x equals 25. I can double check that that works. 25, if I plug it in here, times 3 is 75. 75 plus 6 is 81. So right now I'm thinking, if I'm checking it, I have 4 times the 4th root of 81. So what number times itself 4 times equals 81? I know because I did it over here that 3 to the 4th power is 9 times 9, which is 81. And so I know this is going to equal 3. So I currently have 4 times 3 minus 12 equals 0. And obviously 4 times 3 is 12. 12 minus 12 is equal to 0. 25 works, okay? And so that's how we're going to handle these fractional exponents. I have for you 4 more practice problems. You can feel free to give these a go. You do not have to. If we were in class, we would be solving them excuse me, independent of each other, and then I'd be showing the answers. So what I'm going to do here is I'm going to wait about 10 seconds and show each of the answers. That way, if you want to, you can pause the video and go through and do some practice. I would encourage you definitely to do one of each. This one's pretty darn tricky, okay? Because it has those 2 pieces. This one is a lot of work. So I will work through that one quietly, but the other ones I'm just going to show the answers to. So if you want to, pause right now and give this first one a go. So the answer here is 38. Very quickly, I'm going to get my root alone. I'm going to add 1, add 1. I'll have 6 equals the square root of x minus 2. I'm going to square both sides, and that's going to help me cancel this out. I'm going to have 36 equals x minus 2. I'm going to add 2, and I get x equals 38. Okay, let's come down to this problem here, okay? I'll give you about 10 seconds, and then I'll show it, and we'll go over the answer very quickly. So if we're looking at this problem, I'm going to get my root alone. I know this could be rewritten as a cube root. I'm going to add 1, excuse me, minus 1, so I have a negative 1 here right now, and that's gone. Then I'm going to cube each side to cancel my cube root. Okay, now negative 1 times itself 3 times stays negative 1. That cancels, I'm left with 3n plus 2. I'm going to minus 2, which gives me negative 3. Divide 3, which gives me the negative 1 as an answer. Let's hop over to this one where we're dealing with a fractional exponent again. I'll show you it. If you want to, pause the video real quick. Now let's talk about this problem very quickly also, okay? I noticed this right here, only this chunk would be in a cube root. So I'm going to add 2 first, and then I'm going to divide by 3. Now I'm left with a fraction here, okay, which is not great, but it still can be worked with. So I currently have the cube root, right, because it was to the 1/3 power, of 5y minus 1 equals 2/3. I'm going to cancel out this cube root by cubing, and by cubing here, okay? We haven't talked about our exponent properties in a long, long time, but hopefully you remember that if you have 2 things, okay, a fraction here, and it's raised to the 3rd power, you can just cube both of those, okay? If not, you could write 2/3 times itself 3 times and do 2 times 2 times 2, which is 8, and then 3 times 3 times 3, which is 27. Either way, whether you decided to distribute that cube to both pieces or just multiply it by itself 3 times, you're still going to get this solution. So now I'm going to add 1, okay? And this is where we do need to create an improper fraction. So when I add 1 here, I'm really adding a 27 over 27. They have to have like denominators, right, in order to add numerators. So 27 plus 8 is 35 27ths. So right now I currently have 5y equals 35 27ths. That's a mess because I know my last step is to divide by 5. Well, dividing a fraction by 5 is funky. So instead I'm going to multiply by the reciprocal of 5, which is 1/5. And I end up with 35 over 27 times 5, which is a pretty big number. Oh gosh, it's like 100 and I think 35 right there. But I'm not 100% positive. I'm not multiplying that on a calculator right now. What you should have noticed, hopefully, without multiplying those across, is that we can cross cancel here. 5 goes into 5 once, and 5 goes into 35 7 times. Okay, so I could just do 7 times 1, which is 7, and 1, right, times 27, 27. And that's where we get our 7/27ths for this solution. This last one is the worst one, but it's the last one we're going to go over together. So take a second, seriously pause the video, okay? I'll show the answer, but this one's going to take us some time to solve. Now, I know what you're thinking. You're thinking every time you have a root and you add or subtract it to something else and you have a root over here that it's going to be no real solution. Now, that is the case right now with these two problems, but that is not always the case, okay? And what I'm doing is I'm referencing this problem here, which was also a no solution. So let's just make this last one happen right now, okay? It's going to be a bit of a work. Our first step when we're dealing with roots is to get a radical alone on one side of the equal sign. And if you look, this already is alone. So my next step is to raise it to its power. This is a square root. I'm going to square and I'm going to square. I'm going to bring my work over here a little bit. So I currently have x plus 15, that's nice, equals a binomial times itself. So I have 5 plus square root of x times itself. So maybe we'll do that math up here. 5 plus the root of x times 5 plus the root of x. Hopefully right now you're like, oh, I gotta FOIL it. So much work. It is so much work, but it's work you are totally capable of doing. Okay? So first we got 5 times 5, 25. Then we have 5 times the positive root of x, which gives us plus 5 root x. We're going to get the same thing when we distribute this here and here. So 5 times the square root of x is another 5 root x. And then last we have square root of x times square root of x, which is going to be positive square root of x squared, right? Because it's times itself. Those two cancel, and it's really just going to be an x. So what I really have here is I have a 25 from this. I have a plus x outside of a root. Then I have 5 root x's and 5 more root x's. So together I have 10 root x's. Okay, that cannot be simplified any further. Now, luckily, I only have one root left. It's here, right? I did get rid of the one on this side. So I'm going to isolate this by subtracting, and then dividing by 10. So I'm going to minus 25 minus 25. That's going to give me a negative 10, right? Then I'm going to minus 1x. Those are going to nicely cancel. So I'm going to have negative 10 equals 10 root x. Divide. And I get negative 1 equals the square root of x. So remember, negative 1 is not my answer. I got negative 1 equals the square root of x. Last step, cancel out that root by squaring. So cancel. I got x equals negative 1 squared, which is positive 1. So I'm feeling great about that answer, okay? So I need to plug it in and check. And I didn't plug it in and check here. Well, I did here and here, but I didn't do it here. I skipped that for whatever reason, probably because it was a fraction. But I should not have, right? Because that's how I prove that it works or doesn't. So I'm going to put a 1 here and a 1 here. 1 plus 15 is 16. Square root of 16 is 4. So right now I have a 4 equals. Then I'm going to plug in a 1 right here, right? Square root of 1 is 1. So I have 5 plus 1. Oh, 5 plus 1 is 6. Does 4 equal 6? No solution. Okay? No solution. Now, I want to point out that if this was a minus right here, 5 minus 1 is 4. We would have had 4 equals 4. We would have had that it worked, okay? It's because this sign didn't jive well with it, okay? This sign did not jive well. So at this point, we are done with this section. You have a lot of practice problems because they can look a bunch of different ways. They could have these fractional exponents. They could just have a root. They could have funky roots. They could have a root equals and then a binomial. Or it could have a root equals a root. If that happens, just square them both and get going on it, okay? I am definitely available for office hours, and I really encourage you, before break, hit me up on those office hours if any of these problems look tricky. I'm happy to do any of the homework ones with you, and we've done a lot of good work, I feel like, during those office hours, okay? Lots of questions answered, lots of people feeling a lot better about it before they had attended. So please consider joining me and joining people in other Algebra 2 Honors classes to kind of discuss this stuff if you have any questions. I am signing off. I will see you folks later. Have a great break if I don't see you. Bye.